Oops, I forgot to mute.
Guys.
Yeah.
Work? Any questions? No questions? Okay, so I'm starting to feel like I could do a quick survey here. Like, about how many questions do you normally do on the homework? Do you do nothing, or do you do 2, 5, maybe all of them? Maybe you can write that in. I just want to have a survey. So if no one's actually doing the homework, then I don't really think there's a point of me actually making anything. So did anyone figure out which question, which answer was incorrect? Anyone? I know Felix did. Okay, so the wrong answer was, it was number 6. So number 6 is with a mass of 10 kilograms attached to a pulley, and then another mass of unknown weight is also attached, and then it gives us the acceleration of 1.7 meters a second squared, and then it asks for the mass. So in the answers, I only put 7.04 kilograms. But you can't assume that the mass is going to be less than 10 kilograms. So there's another solution possible, and that would be 14.2. So number 6 was the wrong answer thing.
Sorry, no, sorry.
Sorry, it wasn't Felix. I think it was Travis who got it right. So for those of you that just came in, the wrong question, the wrong answer on the homework was for number 6. And on that, there is only one solution, 7.04. But you can't assume that the unknown mass is going to be less than 10 kilograms. It could also be greater than 10 kilograms. So the other solution would be 14.2. So you would have to include both of those solutions. I think Travis was the only one who got it right. I'll wait one more minute. All right, let me get going. So I'm going to share my screen. So, if you guys saw my email from last week, we are going to be reviewing kinematics and dynamics today. So before we go on to everything else, such as okay, so before we go on to what we're going to talk about next week, which is going to be circular motion, so things going in circles, we need to review our kinematics and our dynamics to make sure we get them right, all right? Because these things are going to have to carry on for all of physics. So I think it's important to at least take one class to review all of these. The topics we're going to discuss today are, first, we're going to review our kinematics, then we're going to review dynamics, and then we're going to have quite a lot of review problems. All right, so that is basically it for today. So, kinematics. So first off, we're going to start off with the most basic things that we need to know, which are basically the definitions of velocity, right? Velocity is change in x over time or displacement over time, okay? And the same thing goes with acceleration. Acceleration is the change in velocity over time, or if you have a starting acceleration, starting velocity and an ending velocity, the difference of those over time, that would be our acceleration. So those are the definitions of acceleration and velocity. So we have two major formulas for kinematics. We have the first one, which is v squared equals v0 squared plus 2ad. All right, this one's pretty important. And then we have the other one, which is d equals v0t plus 1/2 at squared. So these two formulas, you should have these down already. And if you don't, please take maybe a screenshot or something of the screen. So these are basically the crucial formulas we need to know for kinematics, okay? So for one-dimensional motion, all you need to do is just take what the problem gives you and apply these formulas to them, okay? So now what about 2D kinematics? So for 2D, sometimes we're going to have a velocity at some kind of angle. So the crucial part about 2D kinematics is to divide our velocity into x and y components, right? We can't just add vectors when they're not in the same direction. So we need to divide them into x and y components. So that's basically the most crucial part of 2D kinematics. Another crucial thing to know is that x and y components, or whatever kinematics is going on in those directions, have no effect on each other. So whatever is going on in the x direction, that doesn't matter to the y direction. All right? And then here's something you can remember also. Vy is just v sine theta, right? Because of the right triangle we can make here. And then we have Vx as equal to V cosine theta. That's just a pretty cool thing to remember. So 2D kinematics is all the kinematics formulas just applied to 2 dimensions. All right. Another thing to know is that the amount of time a projectile is in the air only depends on its vertical component of velocity. Okay. So the amount of time something's in the air, only the vertical component of velocity, and all the kinematics in the vertical direction, only those matter. And we also have a pretty helpful formula here of the horizontal range formula, which is v0 squared sine of 2 theta over g. So this is the horizontal distance a projectile will go if it's launched from the same height as where it lands. Okay? So if it lands any lower or any higher, then we can't use this formula. But this one is pretty handy if we're going to be talking about kind of specific problem, okay? So these are the things we need to know for 2D kinematics. So now we're going to review some dynamics here. So the most crucial formula for dynamics is the sum of all forces equals mass times acceleration. So what do I mean by sum of all forces? Force is a vector, right? So if we add all these vectors together using vector addition, then that force vector, the final sum of all those forces, is going to equal to our mass times our acceleration. Another way to write this is our net force equals ma. So we have to add all the forces acting on an object to get this value, and that would equal to mass times acceleration. This is the second law. And then we have the third law, a really sneaky law. As we know, we cannot forget the third law. The third law means every action has an equal and opposite reaction. So whenever you're doing problems with the third law, you always have to look out for what we like to call third law pairs. All right, so if one object is exerting a force on the other object, then the other object will exert an equal and opposite force on the other object. Okay, so this is the sneakiest law. Always try to look out for these. Okay, and then we have a few other definitions here. We have the weight of an object as equal to its mass times gravity. And normal force is the force an object, a surface exerts on an object upwards perpendicular to the surface. All right, it has to be perpendicular, normal force. Okay? And so with normal force, we also have our equations for friction. So our kinetic friction, that frictional force, is equal to our normal force times some kind of coefficient of kinetic friction. For our static friction, this is less than or equal to our normal force times some kind of coefficient of static friction. What does that mean by less than or equal to? Well, just to clear up things a bit, kinetic friction is the friction that applies to any moving object. So as long as an object is moving, kinetic friction will apply to it. And it is always in the opposite direction of the object's velocity. Static friction is the friction that if the object is at rest, this is the friction that's preventing the object from beginning to move. So if we have some kind of cup, for example, on a table, we all know that we have to exert some kind of threshold of force before a cup will start to move, right? If we push the cup with just a teeny tiny force, it's not going to go anywhere, right? So what's resisting the cup from moving is going to be static friction. And static friction is also going to be teeny tiny in this situation. If we exert just a little bit more force, but the cup still doesn't move, static friction has increased a little bit as well. So that's why we have this less than or equal to sign. And then we hit a maximum static friction force, which is given by this formula. So this is the maximum capable force that static friction is going to be able to do. So if we overcome the static friction force, then the cup will start to move. So that's the definition of static friction. So now for common applications of dynamics, we have first one, which is the pulley. Right, we're going to have some M1G pulling down. Right, and then we have tensions in the rope. And just to review tension one more time, tension is the force inside a rope. Okay, it's just the force inside it. And tension is the same value throughout a rope as in dynamics. Okay, so if we have some kind of tension in a rope, it's going to be uniform throughout the rope, and this value of tension is going to be present throughout the rope. Okay, and another common application of dynamics is the inclined plane. For some angle theta and some box resting on it, there's going to be a downward parallel to the plane. The force pulling this box parallelly to the plane is going to be mg sine theta. And then the normal force, or the box going into the plane, this is going to be mg cosine theta. This is the normal force. If there's nothing else on the box or any other force on the box, this is going to be the normal force. And so our friction is going to equal to our normal force times whatever mu that is, which means mg cosine theta mu. Okay, so those are the components of any inclined plane. And our final little tricky thing is stacked blocks. Okay, so if you guys were in the last lesson, I don't think I need to explain this. but if anyone wants me to, I can do that. So does anyone need me to explain stacked blocks? So the key for blocks is just to consider each block as itself. Okay, so we're going to do all the forces on this blocks, and then we're going to go to all the forces on this block. Okay, so that's the key part of stacked blocks. We consider each block as its own self, and we look at the forces on that box. So that is all we need to know. So let's go on to these wonderful problems for the rest of class. So this is going to be pretty hardcore. All right, so let's get started here. So first we have these three 1D kinematic problems. And as you can see here, we have some kind of timestamps on them. So that's the amount of time I expect each problem to take for you guys. So that means I'm going to wait for 4 minutes for these three problems. So once you get an answer, please private chat that to me. Okay, so that would be 4 minutes. So I'm going to go through these problems now. So for the first one, we have a 2-kilogram ball dropping from a height of 100 meters on planet Z. If it falls on the ground in 10 seconds, what's the weight of the ball on this planet? So this is kind of a fusion between kinematics and dynamics here. We have weight. The definition of weight is the mass times gravity, right? So on planet Z, we already have the mass. As long as we can find the acceleration due to gravity on planet Z, then we'll just have our weight. So how do we find the acceleration? We have a distance, we have a time. So that asks for this equation, d equals v0t plus 1/2 at squared. So in this case, v0, it's just being dropped. So v0 is nothing, 0. So we can just eliminate that essentially. So now we have d. So to solve for our acceleration due to gravity, we'll just move everything to the other side. So it'll be d over t squared times 2. That's our acceleration. Okay, so solving that, we have 2 times 100 divided by 100, which will equal 2. Now we have this. We'll just do 2 times 2, because 2 is our mass, and then 2 is our acceleration, 4 newtons. That's the weight of the ball. Okay. Now for the second problem, Bill can throw a ball vertically at a speed 1.5 times faster than Joe. How much higher will Bill's ball go? Well, this question is a little bit abstract, isn't it? Well, looking at our kinematic formulas, we have this one. All right, so since we have a difference of velocity here, and we have a constant acceleration, then all that means is that now we can solve for the difference in how high it would go. So in each case, our initial velocity is going to be v0, and at the end it's going to be v, which is 0, right? At the top, it stops. And by that point, it's going to have traveled some distance d, right? So since this is 0, if we establish a positive and a negative, we have our a as d, and it's negative. So now we're going to have v0 squared equal to 2gd. So looking from this, we have 2 and g as a constant, right? So now we have v0 squared as proportional to d. So a fancy way you can write this is with this kind of weird symbol. v0 squared is proportional to d. So what does that mean? If we throw v0 at 1.5 times higher, then that's going to be 1.5 times the distance, because these two are in proportion. So that would just be 2.25 times the distance. This would be how much higher it would go. Now I have the last problem. A rock is dropped into a sewer and the sound of it striking the water is heard 3.2 seconds later. If the speed of sound is 340 meters a second, how deep is the sewer? Well, first the ball will drop down. That's going to take some kind of t. And then the sound is going to have to go back up. That's going to take another t. Let's label these t1 and t2. So how long will it take for the ball to drop down? Well, I can use this formula here. D equals v0t plus 1/2 at squared. Since v0 is 0, then that gets eliminated. And the amount of time, which is t1, time equals 2d over a, the square root of that. And in this case, a is just g, right? So this is t1. So how long does it take for sound to get back up? Well, it's going to be going up at 340 meters a second. And using the formula where v equals d over t, then the amount of time to solve, that would be t2 equals d over v. So, as we know, in total, this is going to take 3.2 seconds. So t1 plus t2 equals 3.2. So that means the square root of 2d over g plus d over v equals 3.2. So now plugging v in as 340. Now we just have a quadratic that we need to solve. Okay, so I'm not going to solve the quadratic right now. So once you have this equation, you can just solve for D. All right? Are there any questions? Alrighty. Let's go on to number 4. So for now, I'm going to skip number 5. Maybe I'll include that in the homework. This is actually very similar to number 2 on the last slide. So this shouldn't take that long. Okay, I'm going to explain this one now. So you throw a ball up and you catch it again, and it is in the air for a certain amount of time. So now you throw it again, but this time the ball is in the air for 3 times longer. What percent greater was the velocity of your second throw than the first? Well, if we see time here as in this problem, then we're going to think of the equation d equals v0t plus 1/2 gt squared, right? So in this case, if we have, so the ball's going to go up as some kind of v0, and g is going to pull it down. So in this case, let's just put g as negative. Okay, so now we have this equation here. So since we're throwing it up and catching it again, then our displacement is 0 because it hasn't really gone anywhere. So then if we move v0 to the other side, v0t equals 1/2 gt squared. And now if we divide through by t, we get v0 equals 1/2 gt. All right? So as you can see here, 1/2 g is a constant. So v0 is proportional to t. If we use our symbol here again, v0 is proportional to t. So if we have a 3 times longer, then that means v0 is 3 times as fast. All right, so this is 3 times, which means 200% greater. Any questions? Good. Now we have 2D kinematics. So I'm going to give you guys 4 minutes to do these. Okay, so that would be 4 minutes. So for the first problem, a ball is launched from ground level to the top of a skyscraper 100, I don't know what that number, 195 meters away horizontally. Be 195 here, and then it's going to be 155 meters tall. If the ball lands on the top of the skyscraper, what's that number? 7.6 seconds after launch. Well, what was its initial velocity and magnitude and direction? So when the ball is launching, it's going to be at some velocity and an angle theta, right? It's going to have some kind of x component of velocity vx, some kind of y component vy. So as we know in 2D projectile motion, there's no acceleration in the x direction. So that means our vx is going to stay constant throughout the launch. So in the 7.6 seconds, our vx is going to bring this ball going at a distance of 195 meters horizontally, right? So we can just apply this formula, v equals d over t, right? So in this case, it's going to be vx and dx, like horizontal velocity and horizontal distance. So then just plugging this in, our vx is just 195 over that 7.6 seconds. So what is that going to be? 195 over 7.6, 25.66. Okay, so that's our horizontal component of velocity. So that's part 1 done of this problem. So now we need to find the vertical component of velocity. So now we have time and we have vertical velocity. So now we can use this formula here, v0t plus 1/2 at squared. If we have a positive and a negative here, then our 155 is equal to our vy times our time, 1/2 times negative g t squared. All right, so if we plug in 7.6 as t, 7.6 squared. Now all we need to do is solve for vy. So what is that going to be? 155 plus 0.5 times 9.8 times 7.6 squared divided by 7.6. So our vy is going to be 57.63 meters a second. Okay. So now we have our vy, we have our vx. We can use the Pythagorean theorem to solve for our actual velocity. So that's going to be 57.63 squared, adding to 25.66 squared, taking the square root of that, 63.08 meters a second. Now, what is the direction? Well, that's going to be the negative tangent of vy over vx, because we have a right triangle here. So what's that going to be? Negative tan plus 57.63 over 25.66. So that's going to be 66 degrees. All right. So now for the second one, a ball is shot from the top of a 55-meter tall building with initial velocity 18 meters a second at an angle of 42 degrees to the horizontal. It ends up hitting the ground a while later. How far is it from the launch point? So this ball is at the top of a 55-meter tall building. It's being shot at, what is it? 18 meters a second at 42 degrees. So the first thing we need to figure out is how long this ball is going to be in the air, right? So we have to have our vy and our vx. So what is vy? Vy is 18 sine of 42. So if we calculate that, vy is 12.04 meters a second. And this is going up. So now how long is this ball going to be in the air? Well, we can use the formula again. D equals v0t plus 1/2 at squared. So if we establish a positive and a negative, then we're going to have our 55, negative 55, as equal to our initial velocity, which would be, what is that, 12.04 times times time plus 1/2 negative 9.8 t squared. Okay, so now all we have is a quadratic. We can solve for the amount of time this is in the air. So if I move everything to the other side, I'm going to have 4.9 t squared minus, so let me do that, minus 12.04 t minus 55 equals 0. So at this point, you can use the quadratic formula, or if you have a quadratic program on your calculator, you can use that. So I'm going to use my quadratic formula right now. So what's the amount of time it's in the air? Well, it seems like 115 seconds. Well, that doesn't seem realistic. So maybe I've made a mistake here. I don't know what it is. So if you were to solve for time, then the horizontal displacement you would get would just be Vx times time, right? And then you can use that with the Pythagorean theorem to find your distance from the launch point. All right. So I might have made a mistake there on the way. So are there any questions about the approach to this problem? Okay, so now we have a few problems related to the range formula. Okay, so I'm going to explain these now. So these are basically just applications of the range formula. So just to recap this is going to be, displacement is going to be V0 squared times sine of 2 theta over G. All right, so now we have this problem here. Our displacement, we want it to be 40 meters, and our initial velocity is going to be 26 meters a second. So now we just need to plug this into our equation. 40 equals 26 squared sine of 2 theta over G. Now to solve for the sine of 2 theta, I'll get 40 times 9.8 divided by 26 squared. So my sine of 2 theta is going to be 0.55799. Okay, so that's going to be the sine of 2 theta. But we must realize here, we can't just take the negative sign on both sides, because if we just take that, our calculator is just going to give us one solution here. It's going to be 35.44. There's another solution. If we look back at the unit circle here, one solution is going to have a sign of whatever value we got, but then we can have another solution here, which will give us the same sign value. And this solution, if we have a theta here, it's going to be a theta again. So that's going to be 180 minus theta. So our first solution for 2 theta is going to be 35.44, and the other one is going to be 180 minus that. So let me do that. 180 minus that. That's going to be 144.55. So that's the other value for 2 theta. So now if we divide through for both of these values, one solution is 72.28 degrees, and the other solution is, I'm going to do that quickly, that's going to be 17.72 degrees. Okay, so the crucial part of this problem is to realize that there are 2 solutions here, and we have to look really carefully for them. So now the second one, I'm going to use the range formula again. D equals V0 squared sine of 2 theta over G. So what's this going to be? We're going to have an angle, and we have our displacement, and we're going to try to solve for our velocity. So just plugging this in, we're going to have V100 equals V0 squared sine of 2 times 37 over 9.8. Now solving this, I'll do 100 times 9.8 divided by the sine of 2 times 37 and take the square root of that. 31.92 meters a second. 1.93 actually. Okay, so these are basically just applications of the range formula. Now I have the dynamics problems. So I'll give you guys 3 minutes, maybe 4 minutes to do these. All right, I'm going to explain these now. So for the first problem, we're just going to use the definition of weight as mass times the gravity. So now we have, I think that's a 5 kilogram object, which would mean the weight is going to be the mass equals 5 times 9.8, 29 newtons. All right, and if this box is put on a surface, what normal force acts on it? Well, since it's not moving, the normal force will completely balance out our weight. So normal force in this case is going to equal to mg. So again, 49 newtons. Now for the second one, a child pulls their 15 kilogram wagon with a horizontal force of 20 newtons. 20 newtons, and we're 15 kilograms. If the wagon moves at a constant speed, what is the coefficient of friction between the wheels and the ground? So whenever an object is moving, it's going to have some kind of kinetic friction opposing its movement. So in this case, this wagon is moving at a constant speed, which means zero acceleration. And what does zero acceleration mean? Zero force, right? Because if acceleration is zero, then that means there's no net force acting on this object. If we take a positive and a negative, we have our net force of 0 equal to 20 minus our friction. Okay, so what is our friction force? 20 newtons. So what is friction again? Well, that's going to be our normal force times mu. And what is our normal force in this case? Well, the box is not moving up or down in any direction. So normal force will completely balance out mg. So normal force in this case equals mg. So mg mu equals 20. So now plugging those values in as 15 as mass and then 9.8 as g, then we can do 20 divided by 15 divided by 9.8. Mu equals 0.136. Okay? So now for the last problem, I pull upward on an 8 kilogram box initially at rest with a rope. It is observed that the box will travel 10 meters in 3 seconds. What is the tension in the rope? So I'm going to be pulling up at some tension, and gravity is going to be pulling this down, right? So we're going to have some kind of net acceleration that's going to move this box 10 meters in 3 seconds. So what does this mean? We're going to use our kinematic equation here. D equals v0t plus 1/2 at squared. So if we establish a positive here and a negative here, then our displacement will be positive as 10 meters. V0 obviously is nothing because it's initially at rest. So all we have is 1/2 times a times 3 squared. So now to solve for a, I'll have 10 times 2 divided by 9, 2.22 meters a second squared. So this is the net acceleration of the box. So now this acceleration times its mass will equal the sum of all the forces, right? F equals ma. So ma equals F in this case. So 2.22 times 8, 17.76 is the net force on this box. So what are the net forces? Well, tension is positive, mg is negative. So the net force is going to be T minus mg. So now just moving mg to the other side, I'll have 17.76 plus 8 times 9.8, 96.16. Okay? So that is how you would do those. So I'm running a little low on time here, so I'm going to skip these. And let's do these two problems here. So these are applications of dynamics. Expect these to take 5 minutes. So I think I'm probably going to put the problems will be skipped in the homework for this week. All right, so we will be able to do those after class. So I know some of these problems, like both of these problems actually, I haven't specifically taught you guys how to do these. So the point here is to try to use your knowledge of pulleys and all that initially to try to figure out how to solve these problems. All right, so I'm going to go over the first one now. So we have a diagram given to us with a pulley. So now, what I like to do is I like to stretch this out on a flat plane, essentially. All right. So we have a 3 kilogram times g, right? A 3g pulling this way. All right. And in this case, 8g is not under the influence of gravity. There's no 8g force pulling it this way, right? Because it's on a table. So the normal force will balance that out. But then we have a friction here. So this friction, the blocks want to slide down, right? So friction is going to be opposing the motion. So we're going to have some kind of friction here, which will equal to our mg times mu, right? Because there's nothing else on this box, so the normal force must be equal to our mg. So other than that, all we have left are the tensions within these ropes. And we all know that those are going to balance out. So we can use, like, essentially turn this into one mega block of 11 kilograms. So we have 3g pulling this way, mg times mu. So let me calculate that real quickly. 8 times 9.8 times 0.2. 15.68 force pulling that way. So what's the net force? If we establish a positive and a negative, that's going to be 3 times 9.8 minus 15.68, 13.72, right? That's net force. So this is going to equal to our 11 times acceleration. So my acceleration is going to be 1.25 meters a second squared. So now this 8 kilogram box needs to move 1 meter. So now we can use, so it's asking for how long it takes. So we can use kinematic formula here. D equals V0t plus 1/2 AT squared. In this case, V0 is 0 because it's starting at rest. And so our 1 meter is equal to 1/2 times 1.25 times t squared. And solving for that, I'll do 1 divided by that times 2 square root. The amount of time is going to be 1.27 seconds. Okay? So now for the second one. This one is actually a really tricky problem. First time I saw this kind of problem, I was stumped. I was absolutely stumped. So we have a fuzzy dice. And the car, as the car accelerates forward, as we know, stuff in the car is gonna move backwards, right? So this is asking for, while we're accelerating, what's the angle that this fuzzy dice makes with the horizontal, with the vertical? So it's gonna ask for this kind of theta here. So in the reference frame of the car, everything's gonna move backwards, right? And that's gonna be equal to the car's acceleration. So essentially, in the reference frame of the car, as we're seeing it, the fuzzy dice in the car, it's going to be accelerating backwards. Okay? So, MA. So what is the A? Well, it's given by this statement here. The car is going to accelerate forward for 6 seconds until it reaches a speed of 28 meters a second. So that's just going to be A equals change in V over time. So what is that? That's just 28 over 6. So our acceleration here is 4.667. Okay, so it's going to be pushed backwards. All right, and now we can consider the downward gravitational force, mg here. Okay, so we have an ma, essentially the horizontal acceleration of the car, and then we have mg here. So ma, mg. All right. So now we're asking for this theta here. Well, we just have a right triangle. If we were to move mg and turn it into this length, we just have a right triangle. So the negative tan of theta is just going to equal to ma over mg, or just a over g. So in this case, we can see how mass is irrelevant in this problem. So we're just going to take the negative tangent of 4.666 divided by 9.8. It's going to be 25.46 degrees. Okay, are there any questions about this one? So the two parts of this problem was looking at the acceleration of the car and taking the reference frame of the car as acceleration of the dice backwards, essentially. And then we're going to have the downward gravitational force. And these two vectors create a triangle. And using trigonometry, we can then find the angle theta. So these are the last two problems for today. All right, so right now it is 9 p.m. as for my time. So if you guys really need to leave right now, then feel free to do so. But I'm going to explain these two problems now. So at first, for the first problem, you see that we have 3 blocks here. Wow, that's a lot of blocks. What do? Well, since all these blocks are moving together, we can basically consider them as one big mega block of combined mass of 2 plus 4 plus 8, 14 kilograms. Okay, so then we just have our force, and then an opposing frictional force that's going to try to resist our motion. So since this block is moving at a constant speed, then that means these two forces are going to balance out, right? Because if the net force is 0, then the net acceleration is 0. So in this case, our net force is going to equal to our frictional force. What is frictional force? That's just normal force times mu, which is equal to, in this case, mg times mu. Because since it's not moving up or down in any direction, then our normal force will have to completely balance out the gravitational force. Okay, so now we have our force as equal to mg mu. Plugging this in, 14 times 9.8 times, what's the mu? 0.3. The net force will be, and let me just write this in, 41.46 newtons. 41.16, sorry. All right, and now for the last one, this problem is a combination of pulleys and inclines. So if we analyze the situation here, this 5 kilogram box is just like a normal pulley. It's just being pulled downward at 5G. But on the 6 kilogram box, we're going to have the parallel downward force of mg sine theta. Okay, and then we have frictional force. So this system is going to start to move in one certain type of direction, right? It's going to move this way or it's going to move this way. Right now, we don't know. So how do we figure out which direction the frictional force is going to be in? Well, in this case, we can just guess, okay? So I'm gonna show you what happens if we just guess, okay? If I just guess that, I'm gonna guess it's gonna go this way. So that means frictional force is also gonna be this way, mg cosine theta mu. Okay, we can just guess in this situation. So what's this gonna be? Well, if we stretch this out like this, we have a 5g force pulling that way. Then we have 6g sine 26, and then 6g sine cosine 26 times 0.4. Okay, so the net force going in this direction. So let's just calculate the net force here. I have a positive and a negative. So it's just going to be 6g sine 26. I'm going to calculate that right now. 6 times 9.8 times sine 26. It's going to be 25.78. Adding to 6g cosine 26 times 0.4. So let me plug that into my calculator. It's going to be 21.14. And then what about our 5g? 5 times 9.8 minus 49. So this is the net force. Okay. So if we add these together, 25.78 plus 21.14 minus 49, negative 2.08. All right, so what does this mean? Force is negative? Well, since we've established a positive and a negative here, this just means that the force is going to be going this direction. All right? So now, that means that the system is going to accelerate in this direction. So my force equals ma. So what is my acceleration here? Well, we could just treat this as 1 megablock of mass 11 kilograms. So just dividing 2.08 by 11 will give us our answer. A equals 0.19 meters per second squared. Okay? Are there any questions? All right. So that will be it for today. So for the problems we skipped, I'm going to put those in the homework. So I'll see you guys later. Next week, we're going to be talking about circular motion. So that would be spinning a ball on a thread, or Ferris wheels, or maybe even roller coasters. All right. So it's going to be fun. So I'll see you guys next time. Bye.
Bye. Thank you.
Bye.